So let's wait 5 minutes for Approve to join. If not, we'll start with our remaining session. This is going to be the last interaction session for today. I am informed that the course is coming to an end. So yeah, let's get on with it in 5 minutes. Okay, hi Apurva. So let's start our
Yes, sir.
session today. Yeah. So let me start my screen sharing. So I last time I was kind of towards the end, I was kind of going very fast for things. Let's try to properly do this code this time. So now you have a feel for what are we going to do in this session, right? We are going to look at uh, the problem of this simple harmonic oscillator, the damped case. Uh, yeah, let me open my Jupyter notebook session. Open by now. Any? Do you have any questions or some discussions that you need to have?
So like yesterday, I was going through the code which you were writing in Python. So again, there was What I want to say is that again, it didn't involve anything related to like it didn't use any
Physics.
governing equation of vibration. That's what I want
Yeah,
to
yeah.
say.
So that part of it we are going to do now. So first of all, I wanted to contrast. This normal neural network approach, and then try to understand what would a physics informed neural network would be. Okay. So yeah, that's part of the that is something that we are going to do today. Just give me a second. Twitter and the classic. And do you have a feel for how would we include or how would we bring in physics into it? Do you have a feel for it?
No, sir, I have no idea about how to do this because I'm
Okay.
absolutely a beginner in machine learning.
Yeah, that's okay. Maybe then I'll spend some good amount of time on this loss. Basically backpropagation. Let's do it properly. Yeah. So I would open this. Which one did we open last time? I think this is the one. No, not sure. Let me check. So when is when is the exam for the course?
I think it's on 26th.
26th. How was your feedback?
Yes, sir, it was good, sir. But very lengthy
You know,
course.
you can
I
give
have
me
to admit.
yeah, you're saying something. Sorry.
I'm saying a very lengthy course. I have to say.
Okay. In comparison to other courses, huh?
Um, yes, somewhat. I have this feeling.
Okay. What about these sessions and some feedback?
Yes, sir, those were really nice. Got to learn a
No,
lot.
some critical feedback.
Critical feedback. Uh, no, I was comfortable with it. There's nothing
Okay.
much. Like I
Okay.
didn't feel very uncomfortable. Initially, it was somewhat fast, but later on, like I referred some other resources also, so I was able to understand finite volume on that also.
Okay. Okay. Fine. So let's first understand what a typical neural network architecture looks like. What are the steps when you're trying to train a model? Before that, let's first understand that what are we first of all trying to do at hand, right? What is the problem that we are trying to solve? So the problem is that you have some initial condition y equals to y at 0 is known, which is 1, and y dash of 0 is known at 1. And this is the position of a simple harmonic oscillator, let's say a spring mass system. And we are trying to, without knowing the differential equation in y is unknown, we have the data for it. We have y of t, some data for it, let's say t comma y at some points, and we are essentially trying to find y of t, right? Now, this is a good place to question why, like, there is no probability in it. And that is partly because we are uh, dealing with a deterministic model, right? Our model, whatever the data we are generating, it's coming out of a deterministic model. In the background, we have a differential equation. And how does that differential equation look like? Look like, looks like, sorry, it looks like this and so on. You know, we can use x or y, does not matter too much. And this is a function in t. So we have some data, And this is the approach. Let's see what is the typical approach in a neural network model. So first of all, let's understand that we are trying to model a function, one input, one output function. Okay. And the neural network we are trying to train is a fully connected neural network, feed forward, fully connected neural network. There are a lot of names to it. And again, we are not experts in this field. In fact, I would rightly say I'm a newbie and a novice in this field. We are just trying to, together with you, I am also trying to understand what this physics informed neural network is, and in the first place, what neural networks are in the. And so this is like a very refresher code, like very refresher code for all that. You realize that this is a very simple problem to deal with, right? This is a polynomial fit at best. If we were to look at a non-neural network approach, right? You need to just fit in polynomial. Yeah, that is essentially what we are trying to do. And so let's get on with it. So the approach follows like this. We construct a neural network with input layer, and we need a number of inputs that this function that we are trying to approximate has, and the number of outputs this input will have. So suppose if for this case, we have our A, M, C, and K as parameters, and those are like, let's say, known. Let's say we know M naught, C naught, and K naught, right? But what if we want to go ahead and do a more general training? This is something that you can try, you can approach from a matter of curiosity once, because this is the last session. You can go ahead and extend our ideas and apply them and see. So what I'm going to say is, suppose these are also some things that are not fixed, and we want to instead learn the overall effect of L of y with these parameters. So let's say M, K, and C. So now M, K, and C becomes parameters in inputs of your equation, and there you would like to have four inputs there, right? But the output, and what is the fourth input? The fourth input is time variable. Output variables will still be one. What if we deal with a system of equations, linear system, right? Suppose three springs or something like that, where we are tracking the position of three springs. Then our output will change to three accordingly. And then this is the architecture part of it. How many number of hidden variables you would like to keep, and this fully connected neural network that we are kind of constructing has equal number of hidden variables in every layer. And then every layer will have, like, how many layers do you need? Then also we have an option of choosing the activation function uh, that we would like to employ, and that is our hyperbolic tangent function. Again, everything is supplied by PyTorch. So we are kind of just working with this library. It's more or less the code to operate this library. Now, this forward fully convoluted starting layer uh, is defined by a sequential function. This is a function, sequential function, where you have what do you say, a linear combination of n inputs, and that results into n hidden number of outputs, and then you use this activation. Okay, and then you similarly go ahead and create the hidden layers also, and see in the hidden layer you kind of have an array of these what do you say? So there are like n layers in this. So we are running a loop in this small array. Okay. And finally, in your exit layer, you have this again linear combination of n hidden and output. So in this final version, you're kind of just summing them up. Okay. N hidden layers into an output. So FCE will only have what do you say? No activation is going to be there. It is only going to be a linear combination of these n hidden outputs. Then we create a function on forward moving. So if you put some input into your this neural network, first it goes through it goes through the starting layer, then the hidden layer, and then the exit layer, and this is your output. This will be your output, right? These are some helper functions. Oscillator gives you the data that we will need to generate to train our model, and this plot function is also that we saw to plot our training. What kind of training is going on? Uh, Now, last time, what did we do? We generated some data, okay, some random data I generated, and then I tried to model it. The way to model it is first you manually seed it because we are going to do it multiple times, and like we are going to run the same piece of code multiple times. And in order to get the exactly the same output, we need to seed our model, seed our library so that we don't start off with random because weights are assigned some random values initially, right? So the initial weights remains the same. For that purpose, we do seeding, and then we decide the number of architectures in this stuff. So let me, yeah, these are the number of hidden variables that each layer will have, and we are working with one layer. Oh, sorry, we're working with three hidden layers. There is also something called as learning rate, which comes in the process of optimizers or backpropagation. So we are using this adaptive, what was it? Adaptive something, which is acronym for, so ADAM is the acronym for that. And there is a learning rate, which basically means how quickly or how fast do you want to move your weights from their initial position, depending on the gradient. So essentially, we are doing stochastic gradient method, something like you must have heard about gradient descent. So this is stochastic descent method. And this file is just to keep the images that we generate out of this training process. So this is just a bookkeeping line. Now we started, so this line we can run, and then we had this loop. Every time we would, what do we do is we first of all remove all the gradients in our optimizer, no initial gradients. Then we put in the data we have and find out the predictions. YH is the prediction. So basically now this is Y of t, where X of data is t, time. And then you calculate loss. A loss is calculated by prediction minus the actual data. And then using this loss dot backward. So you realize that again, these are all PyTorch libraries. So there is this function which you can actually use to backpropagate your losses to fire. I don't understand exactly what these two steps are doing, but essentially there's a backpropagation step, and then this optimizer kind of readjusts your step based on the losses that you have incurred, right? This is something we'll have to look into when we go into depths of backpropagation. Now, and then we generate some. How does this data like how does this training move, right? So what you see is soon after some training, soon after this training and stuff, you'll get some. So basically, as you move ahead, you see some kind of uh, tuning happens. So initially the model is not able to. Uh, the model looks like this initially, but soon it starts to tune things, right? So let's do this one step once again. I'll also remove the data. There's a lot of the data range is very large right now. So let's restrict the range from 0 to 0.5, let's say. So let's say just till 200 or something. And I'll also reduce the range over which we are training. Okay. I'll generate the data from only 0 to 1. I'll take some 500 steps. Else. Yeah, so let's see what kind of, we'll have to run this entire thing once. So up till now we understand what how do we do things with neural networks. There's a question or anything, no? Oh, please zoom slightly. Okay.
Just yes, sir, now
Okay,
better.
sorry. Now it's okay, right? So we have reduced, effectively, we have reduced the area over which we are training, or at least we have reduced it to a very small data set also. And so so that will keep the training speed quickly because we are demonstrating things. Let's not spend too much time on large data, and right. So with that, let me also let me also change the parameters of our model. I'm basically changing it to a like a um, to values which show very nice results. You can choose different values, but that is not important thing. Um, so let's do this stuff first. So now this part, essentially, what I'll do is to do this. I is 0. While is greater than 0. And then let's train things by 1000 is enough. And then also $200. This is fine. Now let's see how the training goes. Hmm. And hello, anyways. Uh, Actually, it does not look that good. Why is this happening? I have to check. Give me a second. What's going wrong here? I don't understand. Hmm. Do you know why that is happening? We were getting longer plots earlier. Uh, Somewhere I think I've changed something. And I'm not decreasing this num. That's stupid. Listen. No, it's not happening because of that. What would be the reason to figure it out first? Give me a second. To ruin it. Okay, this is now it's okay. Fine. I don't know what happened. Anyways. Okay, so let's train this once again. Let's see what happens. Okay. You're already know what is gonna happen. That's not something very wait. It's taking quite a time. Okay, it takes some time. You see, slowly and slowly, this will take the value. Uh, it will basically approximate things. Now there are two problems. We see two obvious problems with this model. First of all, the model will surely fail in regions away from the place where our data points are. Okay, it will kind of fail there, and that is quite apparent from this graph also. So let us just see how this training actually looks like if we just simulate it. Okay. No, something is wrong. Okay, yeah, we have not run this. That's yeah. This is how this will look over different training steps. Okay. Now, what we know that this model fails away from regions of what do you say, data availability. So what can we do? And one more thing, one very important thing is there's another important thing that we have missed. Suppose I didn't have the data at the initial condition, right? Let's say I kind of chose my data to be somewhat off from my initial condition, let's say. Okay. Then an interesting thing, one unacceptable thing will happen. Okay. At least I presume that. Let's see. So I presume that if your data point, if you don't have a data at your initial condition, then or if you don't train it for your initial condition, then your initial condition will get violated, and that is unacceptable, right? That is not acceptable. So there are two. So you can see that happening, right? Your initial conditions are not met if this in this thing, right? In fact, what you will see is even if I didn't uh, shift the data point from your initial value t equals to 0, you might expect or you might not get t. So say our initial conditions were this, right? Our initial conditions were this. Your initial position was 1, but your initial velocity was 0. Now that won't happen if we would have seen that this will not exactly satisfy unless you dump it that way. And it will not exactly happen. What you will have to do if you have to do it using as regular ANN or regular NN, you would have to take two values very close to each other, two training data values very close to each other and at t equals to 0. So let's say t equals to 0 and t equals to 0.5 or something, 0.005. So it will kind of understand that in this region the slope is 0. Okay, only then we can expect this training this neural network to work well. And so now what is the issue with this neural network? Fundamentally, the fundamental issue with this neural network is that this is not abiding the physics of the problem. We know that the initial condition is 1, and that is part of our physics there, and that has to be satisfied. Now you would argue that initial condition is mathematics, and we can kind of train it. But suppose you don't have an initial data at near t equals to 0. What if our situation was like this? Let's shift the data, available data, a little bit away. Then let's see what happens. Then you will see that it will go off awfully wrong, and you can kind of expect it. It says that at t equals to infinity, the data goes to your y value will go to infinity, negative infinity, and your t equals to 0, y value is some high value, right? If I choose my data away from your initial conditions, you will see this keep on. This will aggravate. Okay, this problem will not get resolved. And so the fundamental issue with just using neural network on your physical data is that a lot of information that you have gathered over um, years of engineering is not used, as you rightly pointed out. There is no physics in neural networks as such, right? And so this is the training that will happen. At initial condition, you are saying that your y value is negative, which is unphysical. So this is something that you have to look out for. Okay. So now comes the point of physics neural network. What we will do, we will explicitly try to fit the curve for our differential equation. We will try to train it such that it kind of satisfies the differential equation, and that is where automatic differentiation comes in. Okay, so you have to be able to express the derivatives in terms of your model outputs. Now, up till now, what have we been trying to curve fit? What are we curve fitting? We are curve fitting data values. We are kind of minimizing the loss or the error between the actual data and the predicted data. That is what we are doing, right? We should do something else. What can we do? What we will do is I'll just quickly let's write this part. So we'll satisfy what we'll do is we'll take certain values. So how do we? What is the formal way of looking at the physics informed neural network? Is that you take two losses. Okay, you don't just simply take one loss. Let me refer to that paper only. Yeah, this paper. The idea is that you work with two losses, not just one loss. There is and the loss will again be mean squared error, but these will be two losses. One based on the value which we were dealing with up till now, and the other with this f. Now, what f is? F is the differential equation. So f will be this. And you want to kind of minimize f to 0 for all t values. That is what we want to do. That is how you incorporate physics into your neural network. That's it. Okay. Did you get my point, Apurv? Rather than just fitting y of t minus y predicted or y data to be 0, trying to minimize this.
The loss function.
Yeah, the loss function. We add an additional loss function, which is exactly the differential equation. We try to minimize the actual value of our differential equation, and it is supposed to be 0 at all t, right? We try to minimize it, or we try to minimize it. That is what our neural network does. Our physics informed neural network will do. Okay. Now, okay. So let's do this part. Okay. And as you said, as you saw in this paper, I'm not properly spent good amount of time. I'm just trying to show you a formula there. You will see that there are two loss functions, one with u and one with f. So what would you expect that with in conjunction with what we were doing earlier, this loss function, we'll also try to minimize this loss function. But at least in this paper, the approach should not be data driven. at now, it should be boundary condition and initial condition driven. At least that is what I would expect a physics informed neural network to do. It should not be data driven, but the data can either be initial condition and boundary conditions, or it has to be differential equation driven only. Suppose if it is also driven by this loss model, right? This one, can you expect it to work fine? Can you expect this one to work fine? I felt that it will not work fine. You know why? Uh, Suppose if your data has some noise, okay, and some significant noise, you won't be able to isolate the effect of that noise if you are driven by the data, specific data. Okay, there are ways to remove noise from your data. That's true for the fact. But if we are going from a very exact or true sense of a physics informed neural network, just this kind of loss function should work. So MSE should be MSE based on, at least this is what I understood. I would like to argue that this is how it should look like. Let me write PDE for that matter. And boundary conditions. Okay. This is how it should look like. Okay. And even in this paper, it says so. So let's read that part. So where is it? So here, these things denote the initial and the boundary training data. Okay. And this F part. So you see the subscript of U is associated with initial and boundary training data, whereas F is associated with collocation points. So some points over which we will try to satisfy our boundary conditions. Okay, so there will be we will take some external. So what we'll do is we'll not deal with the data points we have, the training data points. We'll construct some collocation points in our domain, and we'll try to minimize the loss, the loss function associated with the differential equation at those collocation points. That is what we will try to do. Okay, so let's do that part. Okay. Okay. So these are our collocation points. Let me write X col. And in the vicinity of 0 to 1, we'll take some 30 points. Okay. And again, mu, k, and w naught. These are the three parameters. Basically, m, k, and c are, like, let's say, known to us. In that manner, I'm just copying and pasting the data, the code from the source I have, but we'll just go over it. Okay. Again, the same stuff. Only the training part will change. So this part, the initialization part, is going to remain the same. No issues there. Take this part also. So you write I equals to 0. Why I have like that? This is not important. So now next part of this is this. Okay. So now in this part, you do these. You take these steps. You follow these steps. Okay. Let me write the steps we need to follow. Okay. So first of all, what do? We have some validation data also. Okay. So another important thing is that, okay. Now, suppose if we were to only base our and everything on based of these three conditions. Okay. Okay. Let's say we even remove initial conditions and boundary conditions for now. If we just work with PDE, what do you think our NN neural network, will it be able to give us a good solution? Let's try that. Let's try that. Okay. Let's try that. So I'll remove parts of which are not required. Okay, so we are only going to work with the collocation points as of now, so that we can train our data with based on this PD some PD fitting. We'll remove other data. So there is a loss with one. Loss one is there. And then in this code, let's see what this code is doing. This code uses auto differentiation. So this, you see, auto gradient. It uses uh, auto differentiation. That is an important part there. First derivative is calculated, then second derivative, and then you include the governing equation. Okay. And you write this part, and then you calculate a loss. Okay, note that in this loss, let's remove me. This will be your loss, right? Governing equation, or let me write that as residual, or maybe governing equation is fine. Governing equation should be zero, right? All the sums of all the terms should be zero. What will be our loss? What will our loss be? Loss will be just loss 2, or let me write loss PD. We will have loss PDD, and let me also write this as loss data. Loss data or whatever. So we'll also have some data, right? Some training data. It's just not that we'll have a PD with us. So we'll have some data also, but we are not using that data as of now. Let's see what happens if we just go by the PDE. Okay, and then we follow this back propagation stuff, and let's calculate this. Okay, this one is okay. Let's do this for every 200, or what was it earlier? 10 points. This is 200. Let's try to see what happens. So, you have any questions till wait, why is it taking so much time? Because of this. Because of this. We were running finite loop. Okay. Let's do it again. Physics where WZ physics. This should be expol. Okay, so let's see the legends. The black line is the exact solution. The neural network prediction is by the blue line. Dots were the training data, and green dots are the data points over which we are trying to satisfy the PDE. Okay. So over 200 iterations, it is predicting 0. In 400 iterations, it is predicting 0. Even at 600, it is predicting at 0. 800 also 0. What is going on? Apurv, what is wrong?
I don't know, sir.
Okay. So it's quite, if you just carefully look at it, you will kind of figure it out. What are we trying to do there? We are trying to minimize f of t. How will you minimize f of t? What is your trivial solution to minimizing f of t? If y is 0, your differential equation is 0, right?
Yes, sir.
So that is what is happening there. So first of all, it is important, it is imperative that we have uh, like initial conditions are a part of your solution, right? PDEs will have, they don't make any sense unless you have an initial condition there. So that is an important part of your physics also. So let's add that. Okay, let's add the data we have on our PDE, right? So how will we do it? We know that So initial condition is, I think, torch. I'll have to see what is the this thing. Wait, let me see. Let me open up my code which I had written yesterday. I don't, I'm not comfortable with this syntax of PyTorch yet. Okay, let's quickly look at it. Torch.tensor requires gradient. So basically, we will need a gradient requirement because we need the velocity boundary condition also there. And then YEC will be torch tensor 1. So this is our initial condition. Then another initial condition we have is torch dot tensor. Okay. So what we'll do there is we'll add additional loss functions. Okay. Compute. We don't have a boundary condition in this case, so why I see prediction will be modeled putting the value of XIC and then loss of SIC. Let's also calculate velocity at y dot ICT will be what? Should I zoom a little more? Here you see again
Yes.
torch dot this thing is there. Okay, now model for velocity we need to do a auto gradient y of ICP and what is XIC? Wait. This is the value at of y like this is the value you need and torch one likes like this ICP and create graph 0 and everything is okay. So loss IC will be what? To take torch of main company and then multiply you add YP minus YIC squared plus uh, this will be YIC, okay? And then you will have Y dot ICP minus VIC. VIC is defined here, it should be 0. YIC should be 1. And this is again squared. And what else? Yeah. And then you just add loss PD. You add loss. The total loss becomes loss PDE plus loss IC. Okay, so let's try. Let's put all these things here. So basically now we are in inducing, like we are bringing our physics and initial conditions into it. So now let's see if this code runs first of all. No, is the issue. These should be floating points. Okay. So this one runs. Let me zoom out a little bit because now we're not running any code or like we're writing a code or anything. So let's see how it happens. 0, 0, 0. But you see some rise at x equals to 0 if you note. But let's wait. Let's see. Okay, so nothing happens. Okay, what is going wrong? Let's try to decipher it. Let's remove the loss of PDE for just time being. Okay, let's see if we have properly given initial condition losses or not. Okay, let me redo it with no PDE losses. Okay, so we are already seeing some training going on. Okay, it's not that we have incorrectly see the initial condition, initial velocity is almost correct now. So we have trained it perfectly, but something else is wrong. Again, and one more thing you would notice is, or let's see, you you you, you remember that earlier also we didn't. There was nothing wrong that we had done when we were adding the loss of PDE. But what you will notice just by arbitrarily we are adding PDE loss with initial condition loss, and for neural network he does not know or it does not know which loss to prioritize, right? So probably because there are larger number of uh, collocation points on what do you say? Maybe it is contributing more to it. So maybe we need to reduce the effect of PD. So let's do some kind of some scaling. Let's do some kind of scaling there. Okay. Let's reduce the effect or the importance of the loss due to PD there. Okay. And see what happens. Maybe go a little more. Let's say 1e minus 2 just to see the drastic effect of it. Okay. Okay. So already you see the effect of loss of PD is that it tries to reduce or pull the solution to a trivial solution. So maybe more amount of what do you say? More amount of scaling is required, or else more amount of training is required. I'm sure if we train it like we are just training it for 1,000 times, if we train it for 10,000 times, I'm sure the solution will try to will move towards the true solution. Okay, that is something that is bound to happen. But in the interest of time, let's suppose that we don't look into it. Let's further reduce the effect of PDE loss. Okay, because there are 30 points and there is only 1 point on this thing. Let's further reduce it to 1e minus 4 and see. Let's see what happens. There's a lot of training and you have to see what will tune it best and all those things. So the training part is actually um, very tedious. Okay, and there is where I think more advanced deep learning or not deep learning, more advanced training techniques come in, right? So already we see the effect of PDE loss is kind of vanishing off. We are seeing that the solution is moving away from trivial solution. So we expect some kind of better tuning in this case, right? Any comments, any feedbacks you can we can keep on discussing during this part of the session, right? So we are seeing some slow. Yeah.
No, sir. You go on, sir.
Okay. So maybe even let's go even further down and further reduction of the effect of PD. The our initial condition should be the first thing that we need to satisfy. That is a very very necessary feature of any model for that matter, be it neural network based or just a simple solver, numerical solver. It should have that effect, right?
Yes, sir.
Right. So another important thing which I'll kind of maybe let's wait for some time. Let's train it for a larger amount of iterations. So already
Training
you
very.
see, hmm,
The training is very slow, right?
yes, compared to the neural network case, the training has now become very slow. And it's only philosophically that we can. Achha, are you commenting on the training of my computer or in general as a comment on of PIN versus NN?
PIN thing. I mean, this
Okay,
thing
so
is very slow.
comparison wise, right?
Yes, sir.
Yeah. So the first thing we are noting is that it is slow, and probably that is because we are trying to find a more sophisticated solution, right? This solution is a curve fit, simple curve fit, but this solution we know has a particular functional form. So out of that is what we were discussing yesterday. You remember that paper on why cheap and deep learning works so well? That is what that paper was trying to hint at. That what you want is a very special function in the large class of functions there is, and that is apparent here. In this case, a large class of functions can represent this, and these can fit this curve, right? At these points. But to fit this, to satisfy the PD everywhere and still fit this thing is it is trickier, right? So let's train it further, some more number of times. Let's see what happens. So the training is definitely slow. And one more thing that we can do with the when the training is a little slow is play with the learning rate. Again, that can be catastrophic. Your model might misbehave, but learning rate is something that we can scale up to see if our training can be moved. Can be improved. So let me work with that also. Let's see what happens with that. So training is a little slow. I would definitely agree with that. But the good news is that I have a piece of code and I know for that piece of code the solution very nicely. And let me show that piece of code next before we further discuss this thing. Let me just run that part of the code also to show you that eventually our physics informed neural network will work very well if we train it nicely and everything. Okay. It's taking some time, but yeah. Okay, so maybe I'll run it on a parallel this thing only, where from where I was just writing my code. Okay, so let me run this part of it. I'm just running it. Okay, oh, it died. Parallelly, I will run it in here also in a different notebook. And let's wait and see what happens with this one. So I'm running it in the background. Let's see. Okay, so nothing much happened in this case. It will require large number of training points. So this is, let's see, this is 1,000 training iterations, right? Even in the code which I have where that training is guaranteed, the number of iterations is 20,000 iterations you have to run with. Okay. And kind of can't compare them again because there are a lot of things that you can do to improve your training and other things. Like your architecture can be improved, your other things can be improved, right? So that is again a lot of neural network engineering is some like that is our out of scope, right? Okay, let's see what happens here if we are able to train it or not. Is anything happening here? I don't know. Don't see anything happening, but still, let's try it for 10,000 steps. Meanwhile, on this part of it, what has happened? So this piece of code has run. This thing will happen, and we are in the process of running this thing. So let me see. Let me if any data image is generated on this plot, I'll show it to you. Okay. Nothing is happening here. See, in 6,000 steps, this is working very well. Already kind of almost like it's much better than this physics informed this normal neural network away from the points available, right? So the piece of code that we have written right now is not showing any promise, and there's a reason for it. The reason being, in this piece of code, we have taken kind of model fitting of this training points also into account. See, it is very important here. We have not taken into account the effect of the data points. We are not minimizing the effects of like we're not trying to fit in the training points also. You realize that we've not done that. And to be precise, that should not be required. It should not be required, and it is kind of a cheat if you do this. It will give you better training. Definitely, it will help you. It can it is not a cheat, but it kind of drives your neural network to move to the solution. Okay, so there are that will improve your training. So this one, I don't think anything is happening here. So let's stop this. Let's try to incorporate the effects of data also, loss data also. Okay, let's see what happens. Okay, loss data. Uh, okay, so over 12,000 steps, this has also done some nice work over this one. So it's all about trying to drive your solution to like trying to drive your neural network to uh, to the exact solution. That is something that you have to deal with during the training part of it. Okay. As you can see the same code, if you don't incorporate the data points, it becomes very challenging to include it. Okay. To train it. It could become very challenging, so to say. And this code is almost the same piece of code. You see, there is only physics based, the PD based loss and the database loss. So no initial condition losses are there in this piece of code, which to be precise should be there. This one is still not working. Probably because we have given too much importance to this second effect. Maybe it is taking too much we are giving it too much importance. Maybe we should stop that. Wait. That is what we have to train it. Like that is also something that we have to tune every time we are training our model. Okay, let's try this once again. So at 18,000 steps, you see how nicely it is able to get the physics of it. Okay. So let's
Yes.
focus on this. So now you would likely believe that if we train it this way, then very nicely it does it kind of grasps the physics of it. But there's an important there's an important distinction between these two codes and the reason why it's not working. So see, with some tuning, I'm able to get some good training here. Okay, let's see. Nice. So even this one is working nice now. So the weights on initial condition also was required to be reduced. That was hampering with our effect on this PD also and loss data also. Okay, let's see. Oh, it failed. It failed. This one failed. Problem. Fail. It didn't fail. Basically, this line was not executed. So so this one, look at this one. In 1,000 steps, it is able to do. Let's compare this one. In 6,000 steps, this is the performance. In 1,000 steps, this is the performance. More or less, maybe this is a little better, but we'll have to wait till 6,000 steps. Okay. So some amount of tuning is required. So now we are seeing once this proper curve fitting is done, the improvement has slowed down. It's not improving much. Still. Good that our code has at least worked well with comparison to the earlier code I had. Nice. So now the improvement is quite slow. We'll have to wait till 6,000 steps to at least compare the two ways of generating the same physics informed neural network. This is not doing anything much now. Only small changes. See, at 1800s, the error was quite large at 1400, but now it is kind of shifting. It's not that it is not improving, but very slowly. Okay. Uh, you know what? There's a slight like this method will fail. The one on the right will fail because you don't have an initial condition. This method will fail if your data is a little shifted. In this case, also it will fail. I'll show it to you. It might fail. Let's see. Not sure, but let's see. It can fail. I believe. Let me shift the data a little bit because we have not explicitly put in initial conditions there. I believe it can fail. Let's see. Let's run them in parallel. Now we have the same data points also. Some training data points are also same. So maybe this will be a better comparison. So now you have seen once this matching is done, the improvements have gone very slow. But they're bound to happen. Over 2,000 steps, I believe it can happen. We'll have to just wait. Learning rate. So this case is 1 minus p. This one is again 1 e minus p. Compare this one image in new tab with this one. So there is some improvement definitely. In this one, you see a small change at this peak, a crest, whereas you can just see performance has only improved. It's not that it is not doing anything. So we're still running. Okay. So see how, okay, maybe we can compare it this time. Over 6,000 steps, this is your earlier implementation. If you had removed, see, earlier our training data was having like earlier in this right hand side of the code, the training data had the initial conditions embedded in it. Now that I have removed this, see the performance has supposedly worsened. I, I believe in 2000 steps, 20,000 steps, this way of training might not lead to a good model. Okay, but anyways, let's wait and see. So over 6,000 steps, this is the performance, and we are already very close to matching it in 6,000 steps in this case. Okay, now it's just you have to wait and see. Let me just talk to you about other things. This neural network approach. So what did you see? There were issues in the training part of it, right? In the training part of it, there were certain issues. We had to do this kind of stuff, right? Now, and again, the way this is just an illustrative example, right? This is an illustrative example at the end of it. See how the performance away from the training data, away from your training points, is just very poor. Over 12,000 step, it's so poor compared it to this one. Okay, it is kind of, it will approach to, it will give you the exact model, I believe, in 2000 steps. At least I imagine so. Anyways, what was I saying? What is the applicable, like what now, maybe we can have a small discussion. What do you think is the applicability, or what is the practical benefit of this neural network, this specific neural network? Do you see any practical importance to it? At the end, it is just a curve fitting, right?
Yes, and above that, PIN is slow, so no, I don't see much advantage.
Yeah, it's not slow. It's just that we are new to it. We don't know how to properly train it. See, the problem is if you are training it badly, right? As I told you, if we were just to train it based on the PD loss, we would never reach the solution because, and what was the issue there? The issue was, what do you say? That we were not considering the fact that there is a trivial solution better minimize uh, that will better minimize what you say, the loss. Okay. uh, See, in this one it is kind of coming close now, so both the methods will kind of approach the true solution, but this is taking much smaller steps. This will take larger steps. So even with this example, you can see there must exist a better way of training it so that we can reach the solution faster. So just the reason that it's slow is not of much importance also, because you've got a lot of time. It's just that in this course of class we are there for 1 hour, so we feel that we don't have too much time, right? But in the course of time, you can just keep running the model for a day and it won't matter to you, right? So slowness can be an issue. It can also be not an issue, but uh, you have to train more rigorous model. Maybe what we can try, can at least try to, we can attempt uh, training the data for some random value of k, omega, and like these three parameters, right? At least that is something that we can do, right? Uh, but again, then visualization becomes an issue. But let's see. Let's see. So over 2000 steps, this will reach the accurate solution, I believe. See, it's already very close. The applications or the practicality of PIN, I don't know if it is too much. I don't know. Maybe there are applications where physics informed neural networks can help. And definitely they can help. Let's be real here. It's not that it will not help. It will definitely help, right? It's just that we can't actually what do you say? It's not apparent at this point of time with this example. Maybe in some other example, if we are trying to say if we train a model which calculates drag for some random, let's say we train it for a drag, calculating drag for a cylinder, and we can expect some insights if we put some complex geometry into our model, right? Some complex geometry in CFD can be an issue, but for ANN, it can be a strength. For ANN, it does not matter what geometry it is or anything. If it is able to once master the art of predicting the drag behind any arbitrary body, we can expect it to also find drag behind some complex, some unknown geometry. So if we train it well, if we are training it over some large number of data sets, we can expect it to give good solutions, right? It can be a fast way to look at some problems where physics is not that important. We don't want to look into the what is going on. So numerical methods don't the biggest issue with do you realize that the biggest issue with neural network is that you have to go into the depth of everything. You have to you deal with partial differential equations. Sometimes you don't need the solutions to PDEs. Suppose for a drag kind of a problem, for a drag calculation, you just need two velocity fields. Like not even you just need to know how the velocity varies. So I'll just discuss that part with you, right? Suppose there is some arbitrary body and there is a velocity field um, in front of it. And so on. And essentially some sort of you would expect this to happen, right? Behind so basically the wake velocity, but far wake velocity. Let me use the word far wake and upstream flow velocity. Just this two information, just measuring the velocity field far away, far upstream of the of a object and far downstream of an object can give you the drag, right? It can tell you a lot of things. It can also give you, like if we do it in the traverse direction, it will give you the lift. But for a CFD based model, it will have to resolve all kinds of boundaries across this object. Suppose this object is some complicated object, right? Let's say some star shaped, some singularities are there. Let's say this very weird shape. We will have to resolve these very sharp boundaries, some very complicated boundaries if we have to go for a CFD based solution, right? There is no simpler way to look at it, right? So there is the biggest flaw with numerical methods is that sometimes if you don't need too much, you don't need in detail information, some fine information. You don't care about the velocity field at this corner point. You can't proceed with a CFD based solution, right? That is one of the biggest flaws nobody actually discusses. people talk about integral methods and the strength of integral methods, but nobody points out that differential equations have this flaw that they deal with very small, like you have to resolve it over all field, like all of the domain and all of the space to get some answers. So maybe in these areas where you don't need, but again, the success of a neural network is based on the training that you have done. If you have trained it on a generalized data, only then can your neural network be can be validated, right? You can test, you can use the test data to validate, like you can't use the test data to validate it. You will have, and again, no amount of validation can help you there, because essentially you are not working with any physical law, right? It's at the end of it, it is kind of some curve fitting only, right? Some representation that you are able to, you basically some pattern recognition. So if your pattern recognition is generalized, is general, only then you can expect this neural network to work. Suppose this one will work for these three values of k, omega, and n. Sorry, k, omega, and d. This one, these three values, mu and k. This will not work for other values. I'm pretty sure, right? This will just simply fail. Why not? Let's see that. Let's. This one is totally done. No, quite close. If we run it for again 10,000 steps, I think it will approach the solution. So that's okay. Um, let me just let's quickly see the drawback of PNN. This will just simply fail if we run it for some general case. So let's say we have some ten, 500 points. PLT dot plot x comma y. Okay. Let's say not 10, let's say only 3. Okay. And then let's use this one. Okay. So see, we had trained it, like even our governing equation. Let's realize this. Our collocation points were restricted from between 0 to 1. See here. And in this region between 0 to 1, it is kind of giving nice, at least like on a broad level, it is kind of giving good approximation. But outside of this, see how away from this region, it simply fails, just like a simple neural network, right? So even to use this one, we will have to train it for all t values tending from 0 to infinity, and we will have to, okay, again, let's talk about the fact that uh, in the limit t tends to infinity, we know that we have a physical intuition, physics based intuition, that this should go to 0, right? We have a steady state solution to it, right? Y goes to 0. We can enforce that in our neural network, right? And how will we do that? We add additional laws, right? So that's an interesting case. Let's look at it. So just simple stuff. Steady state. Let's say this, and we'll take a x value of what, 1,000, I guess, and we can just put that in there, just like this one. Compute SS loss. So you see that how every insight you have about the solution can indeed be used to train your data. You say here it's YSS to zoom, as you said, to zoom, okay. The YSS 50, so also YSS. Let me check. Right, in away from this region, it simply fails. So we have to, like, our training has to be foolproof. It cannot be simply anything. It's important. V.ss in here, and we just add 1e minus 2 into, or maybe 1e minus in 6 into loss ss. Okay, maybe 1e minus 4, or so let's see how this one works. Wait, one more thing. Let's really increase this to 800. We'll wait for the how does the solution come up. But what you see is that this will fail away from regions of where it has not been trained or collocated. One more thing is that it would fail for other values of k and this thing, d and omega naught. It will simply fail there. If I would have changed the values, maybe we'll see that. Let me train it only for 1,000 steps, not train it for so long. Just 1,000 steps, I think, is enough. Just to illustrate the point that it will fail. Okay. The training has gone down. That is, I think that is because the learning rate also have affected the learning rate there. Okay. But it's quite nice, right? It's quite nice to see how it that solution evolves, right? Very quickly, it's taking up this form now. I think again it will stop the solution. The solution improvement will stop once you don't have once your solution has met all the data points, right? Okay. So in this first 1,000 iterations, this is the best it could have done. Let's see what it does. Again, it's not that much trained so that it gives a good value. Again, the training, that part of it was a very small, weighted by a very small number. And let's see, it will even fail in this region. If we were to just look at this region, what was, let's say, 2 into d naught and omega naught by half. See, it will just fail. Because we have not captured that part of the physics, right? So one more thing is that our training is, as you can see, is a lot of it. The training or the speed with which trains is, it requires a lot of data. If you have a good amount of data, then it can train it very well. So I'll just show that part to U also. So let's just quickly see that also. Let's train it for P, and then let's train it for every 20 points. So we have a lot of data now. Okay. So let's see what it does this time. If you have a lot of data in over a large region, then you can expect good things to happen. So a lot of it is very much dependent on how much data is available to you, because essentially it is data of a fitting. Now the data is a little more spread out, as you can see. And again, at this point of time, we have not trained, our governing equation is still being trained only from 0 to 1. That is also important. Let me change that also. Or maybe run it once more without changing that collocation points. If I do that, so again, the spread has now actually delayed our training, as you can see. It's not very fast. But again, the speed is not the an important parameter. Does not matter to us that much. But then you also realize that if you have to satisfy the governing equation, okay, let's talk about that important aspect also. So essentially, you will have to train the data at a lot of location points, densely put in collocation points. If you have to put in, if you have to force feed the governing equations into your neural network, maybe we need to find a solution around that. So yeah, that is an important, like that is an important issue with it, right? Let's see what is going on there. In this between like 0 to 1, this is fine. All this training is okay, but here it does not train it that well. But important thing is at least our steady state solution is very close to 0. Okay, so if you train it more number of times, that would get reinforced and so on. So I think we have comprehensively, like not comprehensively, with an example of a demonstrate, like with the help of a demonstrative example, we have seen how do we bring in physics into your neural network. Maybe we'll just quickly go through this paper and see what all kind of. So people have done see Schrodinger's equations with this PDE. They've got some good solutions with it, and then people have also tried Navier-Stokes. Let's look at Navier-Stokes. Yeah. So Navier-Stokes, one common state, they were able to predict the pressure values, pressure distribution very well with this neural network. So without actually feeding a lot of, they just fed velocity data, velocity training data, and they were able to get pressure data also. So and they claimed that they didn't give any pressure training to the model. So their claim was without giving too much like no pressure training, we were able to get nice predictions. that was their claim that it helps us. It can do better, and they kind of show how like they can actually identify the differential equation that is going on. So you can actually figure out the governing equation also just with the use of data. So they actually figure out the coefficients in your PDE. They were close to one when they were supposed to be one, and close to 0.001 when they were close to 0.001. So you can kind of also identify PDEs with your neural network, PINN. And yes, so there is another, this is I think some other from some other physics. Can't even pronounce this equation. Burger's equation was also explored. This is Burger, right? Somewhere Burger's equation was, yeah, this one. You know about this equation, right? It's an advection diffusion equation.
Yes, sir.
So that's also there. Yeah. So that I think that is more or less what was about, like what is it about these physics informed neural network. We can again go into details, try to model them better. What we could have quickly done is with this one also, we could have put in this d and omega naught values into our inputs and generated a lot of data over different d's and omega naught and see how well we could have done. How like is it able to like, train over this variation in this two parameters also, right? So that is also something that we could have done. Yeah. So you have any questions or some comments?
No, sir. Actually, I need to revisit. I will rewatch the whole thing again to rewatch.
Uh, so yeah, this course is done, huh? This your all video lectures are done now.
Yes, sir.
Okay. So yeah, I think that's yeah. We'll not meet next time. This will be our final session, so we can see how it matches and other thing. Looks nice. Yeah. So, anyways, as I was saying, we'll not meet next time. If you have any questions, you can try to reach me out. You can just reach me out. I will respond. Or otherwise, yeah. All the best for your exam, and maybe I'll see you around.
Yes, sir.
Okay.
Maybe next year
Maybe next year. Yeah, definitely.
in the campus.
Oh, you're there, huh?
Sir, even this year also I had an offer, but due to personal reason I could not. I didn't join.
Okay.
So
So, which department were you planning to join?
I got offer from aerospace. Sir.
Oh, great. Why didn't you join then?
So I took admission in IIT Bombay, but due to some personal reason, like this, there was some unfavorable circumstance at home, so that's why I could not join anywhere.
Okay, okay.
That's the thing,
I
sir.
hope everything is okay now.
Not really, not much. Slowly, like some health problem is there.
Okay.
Yeah.
I hope everything gets better. Okay.
Yes, sir.
Yeah.
Yes.
And definitely we'll, if you're there, please ping me. We'll definitely meet. Okay. It was nice. Yeah, you turned up every time, every session. It's very nice. Generally, the attendance is always low and on the side of zero. But because of you, I had a record of at least one person being there. It was nice interacting with you, man.
Sir, if you could share your email address, we could be
Oh
in.
yeah. Yes.